of CWPA. I'm a director of CWPA. CWPA is an amalgamation of WCA architects and core associates specialist planning consultants. We merged the two practices there a few years ago, excuse me, and between us we've more than 40 years business experience. I'd like to start by thanking everybody in Irish Aid for their grant support for this project from their Climate Change Fund. Very important that the research be carried out and the studies be carried out and this communication takes place. There'll be two parts to our presentation and then we can have some questions at the end. Shaolima will speak first on building materials and low energy building materials and explore low carbon building materials and explore the ones that are not particularly low in carbon. And then I will speak on low energy design, energy and use. So with that, I'll hand you over to Shaolima and she'll give the first part of the presentation.
Hi everyone, I'm Shaolima Buragohai. Can you guys hear me okay?
Yes, we can hear you.
Thank you.
Oh, okay, great. So I work as a project architect and urban designer here at CWPA. So I'm gonna start with the presentation about zero carbon building materials. So I'm just gonna share my screen here. Can you all see it?
Yes.
Yes, screen.
Okay. So in this presentation, I'm going to go through why we need to use low carbon materials, some examples of zero carbon materials, the difference between the embodied carbon, embodied energy, and how the lifespans of the materials compare, what is carbon footprint, and the challenges of designing low carbon building footprints. So why do we need to use low carbon materials? So the construction industry contributes to climate change through various processes, including the production and transportation of building materials, the energy used during construction and building operations, and the generation of waste. The emissions of greenhouse gases such as carbon dioxide, methane, and nitrogen oxide from these processes contribute to the global increase in atmospheric temperatures and climate change. Additionally, the construction of infrastructure and buildings often result in deforestation and the destruction of natural habitats, further exacerbating the impacts of climate change. So to mitigate these effects from the construction industry on the environment, it's important to adopt sustainable practices such as using renewable energy sources, recycling waste, and utilizing energy efficient building materials. So we are going to discuss 9 different types of zero carbon building materials. The first is blended cement. Blended cement is a type of cement that is created by combining Portland cement with other materials such as fly ash, slag, or limestone. The addition of these materials can have several benefits, including improving the strength and durability of the cement, reducing its carbon footprint, and decreasing the amount of waste produced during production. It can be used as a zero carbon building material in several ways. Firstly, its carbon footprint is reduced because the use of fly ash and slag reduces the amount of clinker which is required to produce cement. Secondly, blended cement can be used to produce low carbon concrete by combining it with other materials such as recycled aggregates or fly ash that has very low carbon footprint. Overall, blended cement has the potential to be a valuable tool in reducing the carbon footprint of a building and helping the construction industry to promote sustainable building practices. Stabilized mud blocks are building materials made from a mixture of soil, sand, water, and stabilizing agents such as cement, lime, or ash. The mixture is molded into blocks and dried to create a durable and low-cost building material. SMBs are considered a zero carbon building material because they're made from locally sourced renewable materials and do not require energy intensive manufacturing processes. Additionally, they have a very high thermal mass, which helps to regulate indoor temperatures, reducing the need for heating and cooling systems. This also helps to reduce carbon emissions related with heating and cooling systems. Overall, SMBs are an environmentally friendly and cost-effective alternative to traditional building materials, and it can be used to help reduce energy consumption and greenhouse gas emissions. Compacted fly ash blocks are building blocks that are made from a mixture of fly ash, a byproduct of coal-fired power plants, cement, and water. Fly ash is a fine powdery material that is generated when coal is burned, and it is typically disposed of in landfills or used as a filler in concrete. These are sustainable and eco-friendly alternative to traditional building materials, as they're made from a waste product that would otherwise be discarded. By using this material, the carbon emissions from the burning of coal are offset, making these blocks a zero carbon building material. These blocks are strong, durable, and fire resistant, making them ideal for use in construction. They can be used in a variety of applications, including walls, foundations, flooring, and roofs. They're also very easy to work with and can be cut to various sizes, making them suitable for custom building projects. In addition to their environmental benefits, these blocks are also very cost effective, as they are made from a readily available waste product. This means that construction projects using these blocks can save on building material costs as well as reduce their carbon footprint. Ramped earth walls are a type of building material made from compacting a mixture of soil, clay, sand, and other natural materials. The mixture is packed into wooden or metal forms and compacted until it becomes solid and dense. These walls can be used to These walls have been used for thousands of years as a sustainable and eco-friendly building material, and they have a high thermal mass, which means they absorb and store heat during the day and release it at night, reducing the need for heating and cooling. They are also very durable, fire resistant, and low cost. As a zero carbon building material, ramped earth walls have a number of benefits. They're made from locally sourced and readily available materials, reducing the energy required to transport them. The process of building ramped earth walls also has a very low carbon footprint compared to traditional materials like concrete and steel. Additionally, ramped earth walls can sequester carbon over time, help to mitigate the effects of climate change. Sandbag walls are a type of building material made by filling burlap or woven polypropylene bags with sand. These bags are then stacked on top of each other to form a wall. Sandbag walls are commonly used as a low-cost alternative compared to traditional building materials, and they are particularly useful in disaster relief efforts because they're readily available and easy to transport. Sandbag walls can also be used as zero carbon building materials because they do not rely on the use of energy intensive manufacturing processes, nor they require the transportation of heavy materials over long distances. Additionally, sand is an abundant and renewable resource, making sand walls an environmentally friendly option for construction. They also have excellent insulation properties, which helps reduce energy consumption in buildings, and in return reduces greenhouse gas emissions, making sandbag walls a low carbon building material. They're a very effective and sustainable option for building construction. Bamboo is an incredibly fast-growing plant that has been used for thousands of years for a variety of purposes, including food, building materials, and household items. Bamboo can be used as zero-carbon building materials because it is a renewable resource that grows quickly, sequesters carbon dioxide, and can be sustainably harvested. In construction, bamboo can be used in place of traditional building materials such as wood, steel, and concrete. Bamboo can be used as a structural material for building frameworks, flooring, roofing, walls, and furniture. It can also be processed into products such as panels, sheets, veneers, and reinforced concrete. These products offer excellent strength, durability, and sustainability, making them ideal for eco-friendly construction projects. It is an attractive option for construction because it is relatively lightweight and easy to work with and is very cost-effective. Additionally, it can be grown and harvested without the use of pesticides, fertilizers, and other harmful chemicals. This makes it an ideal material for those looking to build green and reduce their carbon footprint. In conclusion, it is a versatile and sustainable material that can be used as a zero carbon building material. Its fast growth rate, strength, and versatility makes it an excellent alternative to traditional building materials, helping to reduce carbon emissions and promote sustainable building options. Glued laminated timber or glue lam is a construction material made from layers of wood that are glued together under high pressure. These layers are usually made from soft woods such as spruce or pine and are glued together in such a way that the grain direction of each layer is perpendicular to the previous one, providing a strong, stable, and consistent material. GLT can be used for various building applications such as flooring, walls, roofs, and even large structures such as bridges, schools, and residential buildings. It is also resistant to rot, decay, and fire, making it a durable and long-lasting material for building construction. It is a sustainable and environmentally friendly building material that can contribute to reducing the carbon footprint of construction projects. Prefabricated timber frame system refers to a construction method where wooden building elements were manufactured in a factory and then assembled on site to form a building structure. The wooden elements can be made from sustainably sourced wood and other eco-friendly materials, making them a potential zero-carbon building material. It can be used to reduce the carbon footprint of construction by minimizing waste and energy consumption during the manufacturing and the construction process. By using sustainably sourced wood, it can also store carbon in the building structure, helping to offset emissions from other building materials and activities. It can also be designed to incorporate other zero-carbon building technologies such as insulation, high-efficiency heating and cooling systems, and renewable energy sources such as solar panels. Hempcrete blocks are building materials made from a mixture of hemp sheaf, which is the inner woody core of the hemp plant, along with water and a binder, which is usually lime. They are used as an alternative to traditional building materials like concrete and wood, as they are more environmentally friendly and sustainable. It is a zero-carbon building material as it absorbs carbon dioxide from the atmosphere during its growth, which is then locked into the material when it is used in construction. This means that the use of hempcrete blocks in construction helps to mitigate the impact of carbon emissions on the environment. These blocks can be used as insulation, walls, roofs, and floors. They are very durable, fire-resistant, and have excellent insulation properties. Additionally, they are very easy to work with and do not emit harmful chemicals or pollutants into the air. So embodied carbon refers to the total amount of carbon emissions associated with the production, transportation, and installation of a building's materials and components. This includes emissions from the extraction, processing, and transportation of raw materials, the production and transportation of the products, and the construction process itself. The embodied carbon of a building is an important factor to consider when assessing the overall sustainability and carbon footprint of a structure. The embodied carbon of a material can vary depending on the design projects, but if we compare the typical embodied carbon of these materials as compared to aluminum, steel, slate, cement, and bricks, you can see how the embodied carbon for aluminum, steel, and cement are much higher than these zero carbon materials. Embodied energy refers to the amount of energy required to produce a material, product, or service from the extraction of raw materials, processing, manufacturing, transportation, and construction. It includes the energy used in all the stages of a product's life cycle and reflects the cumulative energy inputs from all sources, including fossil fuels, renewable energy, and human and animal labor. The embodied energy is an important metric for evaluating the sustainability of materials and products and for determining their carbon footprint. Similarly, you can see that the embodied energy for carbon, steel, slate, cement, and brick is much more higher than these materials. Ideal material sourcing distance refers the lifespan of materials refers to the length of time that a particular material can remain functional and usable for its intended purpose. This can vary on factors such as the material's physical and chemical properties, its exposure to environmental conditions, and the frequency and intensity of uses. The lifespan of a material can impact its overall performance, durability, and cost effectiveness, and is an important consideration in product design and manufacturing processes. The building material pyramid is a conceptual framework that provides a hierarchy of materials to prioritize for sustainable building and construction practices. It is based on the principle that building materials should be selected based on their environmental impact, with materials at the bottom having the lowest impact and those at the top having the highest impact. For example, the base of the pyramid may include materials such as locally sourced and sustainably harvested wood, while on top of the pyramid may include materials such as synthetic building materials with a high embodied energy and that has potential for toxicity. By using the building material pyramid, builders and architects can make informed decisions about the materials they use in the construction projects, reducing the environmental impact of the building and the construction industry. Ideal material sourcing distances refers to the distance that building materials should be sourced from to minimize the carbon emissions generated during transportation. The goal is to reduce the impact of the transportation on the environment by sourcing these materials from locations that are close to the construction site. This reduces the need for long distance transportation, which contributes to carbon emissions. An ideal material sourcing distance would be the one that balances the cost of transportation with the environmental impact of long distance travel. So what is a carbon footprint? Generally, a carbon footprint is a measure of the amount of greenhouse gas emissions produced by an individual, organization, or a country as a result of their activities. These activities may include energy consumption, transportation, waste production, and the use of products and services. It is a way to understand the impact of human activities on the environment and to determine ways to reduce emissions and mitigate the effects of climate change. A building footprint is a measure of the carbon dioxide emissions associated with the energy consumption of a building. This includes energy used for heating, cooling, lighting, and powering appliances and other equipment. The carbon footprint of a building is determined by the type of energy sources used, the efficiency of the building systems, and the occupancy patterns and the behavior of the occupants. The goal of calculating a building's carbon footprint is to identify opportunities for reducing emissions and improving energy efficiency, leading to a more sustainable and environmentally responsible built environment. So measures to reduce carbon footprint. Energy efficiency. Upgrading the insulation, lighting, heating, cooling, and ventilation systems in a building is an effective way to reduce energy consumption and lower carbon emissions. With better insulation, the building can retain heat in the winter and cool air in summer, reducing the need for heating and cooling. Energy efficient lighting and modern HVAC systems can also significantly reduce energy consumptions, while improved ventilation helps ensure good indoor air quality and reduces the need for extra systems to provide heating and cooling. These upgrades can have a positive impact on the environment and also lower energy bills for the building owners and occupants. Renewable energy, installing renewable energy systems such as solar panels or wind turbines is a great way to generate power on sites and reduce your carbon footprint. Solar panels convert the sun's energy into electricity, while wind turbines use wind power to generate electricity. These systems can provide a significant portion of your energy needs and significantly reduce your reliance on fossil fuels. Furthermore, these systems have low maintenance costs and have a long lifespan, making them a cost-effective and sustainable solution in the long term. By generating your own power, you can reduce your energy bills, reduce your carbon footprint, and support a clean energy future. Passive cooling and heating systems. These systems utilize natural processes such as solar radiation and airflow to regulate the temperature of a building that are often referred to as passive solar systems. These systems harness the energy from the sun and the natural ventilation of a building to provide heating, cooling, and ventilation. By reducing the reliance on traditional systems, passive solar systems can significantly lower the building's energy consumption and greenhouse gas emissions. Installing green roofs and gardens on a building site can have numerous environmental benefits. Green roofs are covered with vegetation and help reduce the heat island effect by cooling the surrounding area through evapotranspiration. They also help to conserve energy by providing insulation and reducing the amount of heat that enters the building. Additionally, green roofs and gardens can provide habitat for wildlife, including birds, insects, small mammals, and contribute to the biodiversity of the area. Implementing a comprehensive waste management plan is an effective way to minimize waste and promote recycling. This plan should involve the entire community, including residents, businesses, and organizations. This plan should outline strategies for reducing waste, such as using reusable containers and bags, composting food waste, and recycling paper, glass, and plastic. Sustainable transportation. Encouraging the use of public transportation, carpooling, biking, or walking is a great way to reduce transportation-related emissions. These modes of transportation produce fewer greenhouse gas emissions compared to individual car usage, which is one of the largest sources of carbon emissions. Compensation measures. Purchasing carbon credits or investing in carbon reduction projects is a way to offset the carbon emissions generated by your activities. Similarly, investing in carbon reduction projects such as reforestation or renewable energy projects helps to reduce the overall amount of carbon dioxide in the atmosphere, which helps to mitigate the impact of your own emissions and contribute to a more sustainable future. Planting trees or supporting reforestation projects is a simple yet effective way to combat climate change and to reduce carbon footprint. Trees absorb carbon dioxide from the atmosphere and through the process of photosynthesis, reducing the amount of greenhouse gases in the air. Reforestation also helps to restore degraded landscapes, providing habitat for wildlife and can improve the local water life cycle. Supporting initiatives to bring clean energy access to the community that currently rely on fossil fuels is a crucial step in reducing the world's carbon footprint. Clean energy sources such as solar, wind, and hydropower are renewable and produces significantly less carbon emissions compared to fossil fuels. Investing or supporting the development of renewable energy sources is an important step towards reducing our dependence on fossil fuels and mitigating climate change. Renewable energy sources such as wind, solar, or hydropower harness natural processes to generate electricity without releasing harmful pollutant into the atmosphere. By investing in these sources, we create a cleaner and more sustainable energy future for ourselves and our future generations. Supporting educational programs and outreach efforts to raise awareness about the importance of reducing carbon footprint and promoting sustainable practices is also very important to promote sustainability and protecting the environment. By educating individuals and communities about the negative impacts of carbon emissions and other environmental issues, and providing information on simple practical steps they can take to reduce their carbon footprint, these programs can help raise awareness and promote widespread adoption of sustainable practices. Compensation measures are not substitute for reducing emissions, so this measure should be only taken hand in hand with the other measures to in the design phases for building low carbon footprints. The challenges of low carbon building design. One of the key challenges in low carbon building design is the lack of a comprehensive standardized system that can effectively address the unique climate, space, and performance requirements of different building projects. This makes it difficult for designers, builders, and the stakeholders to accurately predict the energy consumption and carbon footprint of a building during the design phase, and to effectively optimize the design for low carbon outcomes. The absence of such a system also limits the ability to compare the performance of different buildings and to measure the effectiveness of low carbon design strategies. Another challenge in low carbon design building is the lack of applicable carbon emission calculation methods for the design phase. This makes it difficult for designers and builders to accurately assess the carbon footprint of a building during the design phase and make informed decisions about how to reduce emissions. This can result in the implementation of inefficient systems and materials that fail to meet the low carbon targets. Another major challenge is the lack of real-time optimization methods during the design phase that aim at reducing carbon emissions. Building design is a complex process that involves multiple stakeholders and requires the integration of various systems and materials. In the absence of a real-time optimization method, it can be difficult to assess the carbon footprint of a building during the design phase and make informed decisions. This can result in missed opportunities and can limit the ability of the designers and builders to achieve their goals. Some of the guiding principles in developing sustainable building technologies. Energy conservation refers to the practice of reducing energy uses and increasing efficiency. Kieran will be detailing in this topic later in the presentation. Minimizing the use of high energy materials involves reducing reliance on materials that require a significant amount of energy to extract, produce, transport, and dispose of, and instead opting for materials with lower embodied energy and environmental impact. Minimizing transportation and maximizing the use of local materials and resources helps to reduce greenhouse gas emissions and support local economies by sourcing materials and resources from within the local community wherever possible. Decentralized production and the maximum use of local skills involves promoting locally based manufacturing and using locally available resources and expertise to produce goods and materials, thereby reducing transportation emissions and supporting local economies. Digitalization of industrial and mine waste for the production of building materials helps to reduce waste and decrease the need for virgin materials, contributing to a circular economy and reducing the environmental impact of the building and the construction industry. The recycling of building waste involves collecting, processing, and reusing construction and demolition waste materials, reducing the amount of waste sent to landfills and conserving resources. Cradle to gate is a term used to describe the life cycle assessment of a product from its creation to the point at which it leaves the factory gate. This type of analysis focuses on the environmental impact of the production process, including the extraction of raw materials, manufacturing, packaging, and transportation to the distribution center. The goal of cradle to gate analysis is to identify areas of the production process that have greatest environmental impact and to find ways to reduce the impact. Cradle to cradle is a term used to describe a more comprehensive approach to life cycle assessment. It includes both the cradle to gate analysis as well as the post-consumer life of the product. This type of analysis looks at the entire life cycle of the product, which includes how it is used, disposed of, and recycled. The goal of cradle-to-cradle analysis is to create a closed-loop system where materials are continuously recycled and used over and over again, reducing waste and minimizing the environmental impact of the product. Both cradle-to-gate and cradle-to-cradle analysis are important tools for understanding the environmental impact of products and for guiding sustainable product design and production. The cradle-to-cradle approach is generally considered to be the preferred system for low carbon emissions in building construction. This approach considers not only the carbon footprint of the building materials and the construction process, but also the ongoing energy consumption and waste generation of the building over its entire life cycle. This enables designers, builders, and building owners to make informed decisions about most environmentally responsible materials and systems to use, with the goal of reducing carbon emissions and creating a more sustainable built environment. The cradle-to-cradle approach emphasizes the importance of designing buildings that are energy efficient, use renewable energy resources, and promote waste reduction and recycling. In conclusion, the use of zero carbon building materials is a crucial step towards creating a more sustainable and environmentally responsible built environment. These materials not only reduce the carbon footprint of the building construction process, but also contribute to a healthier and more energy efficient building over its entire life cycle. The benefits of zero carbon building materials are numerous, including lower energy bills, improved indoor air quality, and reduced waste generation. The use of these materials is becoming increasingly popular as the demand for low carbon and sustainable buildings continues to grow. This trend is driven by both environmental concerns and economic considerations, as the use of zero carbon building materials can help building owners and occupants save money on energy costs and reduce their overall carbon footprint. In order to achieve our goal of a low carbon and sustainable built environment, it is imperative that we continue to promote the use of zero carbon building materials and encourage innovation in this field. By working together, we can create a future in which buildings are not only functional and comfortable, but also have a positive impact on the environment.
Thank you very much for that, Shamalima.
Thank you.
Plenty of very interesting facts in there. I think we're all still online. Ree?
Hello, yes, I'm still here.
Okay, I just said I better check before we go much further.
Okay, no, we're still here.
Great, thank you. I hope you got plenty out of that.
Yes, there was a lot of
on my talk there. So
So we also have a
sorry.
small checklist, like it's not an exhaustive list, but there are few questions that you can ask yourself when choosing material to determine if they're zero carbon or not. So from here, Kieran can start.
Okay, yeah, well, I'll be speaking to you on low energy design. I'm a director here in the practice, and I've more than 40 years experience in private practice. I have a postgraduate degree in energy performance in building, hence the focus on low energy in design. From around 2000 to 2010, the problems associated with greenhouse gases and the damage being done to the environment really it came to light, and people started in this country started to take it more seriously and realize that we've left it very late to be taking action. But at least we're a few years down the line, and it seems to be gaining traction. My talk on design for low energy in use in buildings will cover off with the reason for it being that we need to reduce our energy demand, we need to reduce our carbon generation, and we need to reduce running costs. And hand in glove with that is to reduce energy poverty that people who are living in buildings, in dwellings that are poor energy efficient buildings, and they're suffering the consequences of it. I will call on our experiences in Ireland a lot, and it's a temperate climate. So mostly it's not too warm in summer, it's not too cool in winter. So most of the energy demand will be a heat load as against a cooling load. Things are changing, and legislation is driving big changes, and we've seen them happen rapidly in the last 10 years or so. And with the advent of more efficient buildings, we're now seeing that overheating in our buildings, especially our dwellings, is becoming more of an issue, and a cooling load is starting to take on a role, or either actions to avoid overheating. So the first element is low energy design, and energy is required, as I say, for space heating and cooling, primarily in Ireland, space heating, but office use and that would have a high cooling load. Obviously, different parts of a building require different levels of heating at different times. Living space will typically be heated and cooled during the daytime, bedrooms at nighttime. Schools would be vacant possibly for long periods of the year. Offices are used for typically 9 to 5 and then vacant for a long time. So it's important to get the balance right and to control the heating. Water heating, your hot water demand plays an important role on the energy usage. Lighting, generally now, again, there's been major improvements in lighting with the use of compact fluorescent lamps and light emitting diodes, reducing the energy requirements to achieve the same level of lighting, reducing it drastically. Cooking can be electricity, gas, oil, solid fuels. And then you have plug loads, which are TVs, computers, your washing machines, etc. So the energy source, the largest energy user or source of energy would be electricity in this country. Electricity is generated from a number of sources using oil, coal, gas, and renewables. There's an important point to note with electricity that it's generated at one location and it's used at another. And through transmission distribution of that electricity, it loses a lot of electricity is lost, and there's a conversion factor to represent that. And it used to be as high as 2.08. So in other words, for every kilowatt of energy you use in your house, 2.08 kilowatts had to be generated, and the balance was lost. Thankfully, that's now down. It's now down currently to 1.95, and it is dropping with improvements in technology. The talk is that it should be possible to get it down to 1.5 which is still a lot of energy loss, but it's significantly better than now. So it's the point being that when you save electricity in the home, you actually save twice as much generation. Very important. I said generation of electricity can be coal, oil, gas, hydroelectricity, renewables, and we'll talk about that a little bit more. Oil is still used a lot for energy generation here in Ireland. It's considered a dirty fuel, even though it's highly efficient, and you will get more energy out of oil than you will out of most other fuels. Coal is still used a lot, not so much for heating, but for electricity generation. And it too is considered a dirty fuel, not as efficient as oil, but still quite efficient. Gas, there's a number of gases that are used. They're still used for cooking, for heating, and electricity generation. Gas is still a dirty fuel, but that's not nearly as bad as some of the other fuels available. And its efficiency drops accordingly. It can be as low as 35% for large-scale energy generation, but it can also be up to 91% for domestic heating, whereas oil can be up to 98% if the right elements are put together. You have natural solid fuels, which could be timber, it could be peat. Timber is considered carbon neutral because it absorbs carbon during its lifetime, but it then gives it out if it's burnt. Peat will sequester carbon in its lifetime, and unfortunately, if it's burnt, it gives back the carbon, and then you lose the capacity to hold carbon. Burning peat in Ireland is dropped significantly in recent years, and legislation is trying to put an end to it. And then you have natural sources of energy, mostly from the sun, solar gain, and you also have nighttime cooling. So that when you put all of those elements together and determine how you're going to use them, you can generate energy through renewables. Obviously, wind energy being top of the list, both at national level and local level. Battery storage is a big issue that will significantly help with wind energy when the technology gets to a point that it's viable. The January statistics for Ireland were just very recently published that the highest amount of electricity generated from wind turbines was achieved in the January just gone, significantly higher than previous years, and is growing. They estimate that 350,000 homes could have been powered for an entire year from the amount of electricity generated from wind power. Solar thermal is another form of renewable energy that seems to have run out of favor. There's a large dedicated hot water volume required for solar thermal units. You really have to have a high hot water demand to make it stack up and to make it worth your while. And the solar thermal units have been found to require a lot of maintenance and a lot of replacement. So that they were very popular at one stage. They do generate a lot of hot water. You have to have a use for that hot water to justify it, but their replacement, they were being replaced on frequently, which started to eat away on the financial benefits of it. Solar PV, photovoltaic, on the opposite side of the coin there, is becoming more and more popular. The technology has increased massively in recent years. Typically, a photovoltaic roof-mounted panel would have been capable of generating 180 watts per panel. That's now over 400 watts per panel, depending on the efficiency and the grade of the unit. Typically, the photovoltaic panels are operating between 15 and 22% efficiency, but that's growing at a ferocious rate. And it's seen to be one of the big sources of energy supply of the future. The heat pumps are very popular and are very efficient. They're electrically run, and they generate heat from either air to water, by compressing the air to generate heat that then heats water that's used for circulate around a building. It can be a ground sourced heat pump where you extract heat from the ground, drill into the ground and extract the heat that way. It's very popular, very suitable for low temperature heating, underfloor heating and the like. If you're heating radiators from heat pumps, they tend to have to be low temperature radiators because it's not suitable, for bringing water up to high temperatures, 60 and 65 degrees. It's more comfortable working at 30 to 35 degree range, and it's most efficient there. It's good for cooling. It can be used for cooling, as in your fridge or your freezer. The heat pumps are just a reverse of a fridge, generating heat instead of coldness. They have a coefficient of performance representing the amount of electricity or energy that needs to be put in to the energy that's taken out of it. And again, that figure is growing with technology, improvements in technology, and it's up to 4.5, 5 coefficient of performance, which means it's 4 or 5 times heat is generated from the amount of energy that goes into it. Again, going back to what I said about the conversion factor, you have to remember that every unit of electricity that goes into it actually represents 2.08 or 1.95 as it is now units of electricity to be generated. So it needs to be more than 2 just to break even. But at 4.5 and 5, it's well on that road. The thermal performance of the building, when you have your energy generating heating and cooling and hot water, you have to then look at how do you hold on to that as best you can. So the performance of the building envelope is critical. The walls, the roof, the floors, windows, and doors, and that's typically measured as in the form of a U value for each element. The fabric of the chosen fabric depends or will determine how good the U value will be, and obviously the lower the U value, the less the heating or cooling will escape into the outside temperature. In warm climates, you'll be trying to cool the building and stop the heat getting in, and the reverse in temperate climates. Air tightness and air infiltration needs to be controlled, that you don't lose your heating and cooling through infiltration. Depending on the outside wind pressure will test the leaks in the building more so. When you talk about air tightness, you have to be very conscious of ventilation within the building and habitable or healthy environments in the building, and air quality. And we'll talk a little bit more about that, about controlled ventilation later. Thermal bridging, where you have a highly insulated fabric, but the junctions of floors and walls, windows and walls and so on are now susceptible and can lead to mold risk if you have warm surfaces or cool surfaces that all of a sudden have a weak point in them. It's something that needs to be looked at. The building geometry and the building orientation are very important items as well, and they can be the cheapest of all options to improve the thermal performance of a building, simply by turning the orientation away from, in the hot climates, away from the warm areas, in the cooler climates towards the warm areas, and having your useful solar gains where you want them, and blocking out solar losses. So to turn a building to 90, the same building to 90 degrees could improve its performance. The geometry of the building, the long, narrow buildings with the long edge facing in the wrong direction could impact on the performance, the thermal performance of the building. So to change the proportion would simply improve it without increasing the floor area or decreasing it. The building mass is also very important, and Shawalima touched on that, and a couple of the materials she spoke about, the rammed earth walls and the sandbag walls. They have density and mass to them, and in the daytime they can absorb heat, which they can slowly give out to the building. In the night times when it's cooler, and they can cool down at nighttime and give that heat back into the building in the daytime. So it's a very natural way of regulating the temperature of the building. Building services within a building, their pipework, extract fans, controls, building management systems, all play a role in improving the performance, as does passive stack ventilation. But if you do incorporate passive stack ventilation, it needs to be designed in from a very early stage where the shape of the building would cause it to naturally ventilate itself, and you don't need mechanical extract fans to suck air out or blow air in. The extract fans, or sorry, the ventilation that I spoke about earlier, with buildings that are becoming more and more airtight, humans living in them, cooking in them, moisture is generated within the building, and that can impact on the air quality, and it can also condense if it hits a surface, either on surface of an element, a wall or a floor, or worse still, it could actually condense within the thickness of that element, interstitial condensation. So it's very important to get, the tighter you make a building, the more airtight you make a building, the better your ventilation controls will be. And generally controls, heating controls, ventilation controls play a significant role in the efficiency of buildings in use and energy use. So cost optimization, and this is financial only. It's important to note that this is not weighing up carbon generation or carbon reduction, but all of the elements that you may consider to improve the performance of a building should be analysed by way of a cost-benefit analysis. Now, the cost-benefit analysis will probably show a lot of the time that financially the move doesn't make sense. It doesn't make financial sense. And one of the big drivers of that is the international cost of oil, because once you put that into your calculation, currently it's at a very high level, and it would show up a lot of these measures to be cost efficient. But not too many years ago, when oil was, the demand, international demand wasn't as high and the cost of oil was low, it actually made a lot of the improvements that could be incorporated to be non-viable from a cost point of view. Your replacement costs for whatever element you installed, be it solar thermal or solar voltaic or improved thermal performance, and the maintenance costs may find that an element might take too long to pay back. And in fact, it may be redundant before it's saved you the money. So it's important to note that it's only a financial estimation rather than the true point here to take on board is the carbon saving. And legislation is now coming into place in Ireland, whereby carbon will have a financial cost associated with it. Cars now are penalised. New cars are penalised if they have a high carbon usage. So car manufacturers are looking to reduce the carbon emissions from their cars simply because it's affecting the cost. So again, things will change over time, and we are seeing that change already. So generally on other issues, things to think about and to take on board would be higher skills levels needed and higher knowledge needed by both designers and constructors to make sure we're not creating unhealthy buildings, to make sure that we put buildings together in such a way that they are as efficient as they can be without creating a problem for down the road. Upskilling of professionals and specialist contractors is something that we're seeing an awful lot of here, that the technology is nearly overtaking the skills of the designers and the constructors. In Ireland, building standards are controlled by national legislation. We work to a standard, an NZEB standard. It's near zero energy buildings. It's actually a watered down version of zero energy buildings, but it was when the legislation was introduced, it was considered to be too much too quickly. So the standard was near zero energy standards. There's also a voluntary standard that people may opt for. You're probably aware of it, one of them being passive house standard. Again, a standard that is certifiable if you achieve the standards, and it is a very low energy building where there's no heat load or cooling load allowed in it. The NZEB standard, the national standard of Ireland, is actually very low, and some would argue that it's comparable or possibly even a better standard than the passive house, but you can't really measure the two because they have different protocols as to how they're measured. But it is in new builds, the NZEB standard is quite a high standard to achieve, and is seeing huge improvements. Water conservation is another area that needs to be looked at. Low flush toilets, low pressure showers, use of grey water for irrigation and for firefighting. And that the more grey water that's used, the less potable water, which has a long process to go through to make it potable. So there's definite savings there. And ongoing legislation is coming at us, both nationally and internationally, where this country will be fined for not achieving its targets, its reduction targets in time. And Shawalima mentioned some of the compensating measures that that country will be looking at, as in buying credits where they're available. But buying credit can't be seen as the way forward. It's an emergency solution to it. There's other areas that can be considered, and we see more of it happening, in that international connectivity between countries and their energy supplies is a vitally important piece. Ireland is doing reasonably well on its wind energy production, but when the wind isn't blowing in Ireland, we have to default to our oil and our coal and our gas. There's been recent connections now to the UK, which in turn is connected to Europe, and therefore when we can't produce wind power in Ireland, it might be generated in other countries and we use it, and therefore reduce our dependency on fossil fuels for it. So that's something that big costs obviously associated with it, but it is something that's happening. We also have to look at, well, again, I'm not going to speak about it, but it is happening there. It's more so in some countries than others. Atomic energy, strangely enough, considered to be clean energy until something goes wrong. And hydrogen energy, which is more and more to be read about it as a form of generation. I won't speak about them because I don't know enough about either of them, but we're definitely hearing more about it. So that's more or less the thrust of my talk. And I hope you got some value out of it, and I wasn't too complicated with it. So if you had any questions, you could throw them out now.
Thank you very much, Shamalima and Karen, for that very, very detailed presentation. I will ask if my colleagues have questions, the ones leading the research project. So Mina Palisa Lemo, do you have any questions?
So basically, you talked about REMDF, you talked about, I'll go more into the materials. I didn't really, with regards to compressed F bricks, do you know its carbon emission footprint? Because I saw hempcrete, its lifespan is longer than all the other materials that you had. But I'd like to know more about compressed F, if you have any information with regards to compressed F and materials such as thatch. Have you tested the thermal efficiency of thatch? Do you know its capability with regards to the emission? And also, you said when looking at the carbon emission, you look at the manufacturing, transportation, production of the material, and the end use of the material. So I'd like to know more about materials such as compressed F bricks and also thatch. And also, if you know anything with regards to sandstone, particularly its extraction, how would you go about measuring its carbon footprint emission?
So there are certain formulas that you use to basically calculate the carbon emission, and then the formulas specifically depend on the the design project basically is to get the exact number. It's like, the number varies depending on the various design projects. So for hempcrete blocks, like we have the typical numbers, but like certain products, like their carbon emissions, it varies with the different materials that gets mixed into it, like the overall design elements. So there is not a fixed number, but like if you can tell the footprint calculation.
Yeah. Well, I think we purposely didn't go into that level of detail in the talk. We could provide you with more information, if you like, as in, the calculation, how you would go about calculating the footprint of a material. As Shaolima was saying, we can pull down a spreadsheet with a number on it, as it would relate to Ireland, but you may not be able to use that same product in other countries because it may have a greater transport costs associated. There is a software and calculations that determine what you need to take on board, as Shamalini mentioned, your extraction costs, your transport costs, your fabrication costs, and so on. But again, we purposely didn't bring that level of detail into the talk. We felt it might have been more than was looked for, but we could certainly pass that information on as a separate exercise.
Can I just ask a question? That was a great presentation. Thank you very much. I absolutely agree that there's I wouldn't imagine that there is a requirement at this point to go into that level of detail on that. What I would be looking for, again, a question on the materials, is basically looking at the challenges for each of these materials, the feasibility, the accessibility, the cost. Were they used before? Are they going to be used standalone or in combination with something else? Do they need government approval? Are they going to be sufficient? And to sort of like, to work in parallel with, these materials that you have chosen all look like they are good for the environment and they have low carbon, emissions. But I think that it's fundamental when you're looking at a material to not only talk about the advantages, but you really do need to cover the disadvantages, because at the end of the day, it might not be feasible to use that material. So I would kind of be looking at that aspect as well. Cost is a big factor. Were these materials used before? If so, why are they no longer being used? If they were sort of had evolved to something else, I would be looking at basically all that as well.
Yeah, that's a good point, Celine. And hopefully this talk will prompt a lot of the discussion that you've just mentioned. So some of the materials and some of the items there, they're traditional. They were used for hundreds of years, but they may not be suitable to deliver at scale. Well,
that's it. You see, that's it.
Yeah. And when you sort of drill into it, and I'll give you one example there. Like Shabalima's talk showed that the damage that aluminium and steel can do, reduce a ton of it. So if you think about long span buildings, that really you can only achieve it in steel at the moment, or the likes of a glulam beam, which will span, 10, 20 meters, whatever's required. And a timber glulam beam will give you the structural performance you need of a long span building, and will be far more acceptable from a carbon generation point of view. So you're limited. There's no doubt about it. This is the way the conversation will go. Not everything is going to be suitable at scale. And there are numerous examples of small organizations who have used a number of the materials and have used them successfully, but you won't recreate it at scale, and that is a big issue with it.
Yeah, and I would think that that's very important. Like it's like talking about something that at the end of the day just might not be workable, not feasible for whatever reason, and then this time talking about carbon emissions and going down that road exclusively, I would think, would just serve better purpose if we kind of looked at the materials and looking at cost and scale and availability. Do we need government approval? But particularly to use them at scale, and the insulation and the durability and all these things, and maybe compare and contrast the materials, and then kind of, you know, be always aware of this carbon emission thing. And well, obviously we choose materials for that reason. That's the get-go. And then to basically spend, I think now it's crucial, because there are deadlines to be met, to hone in on the materials and think, okay, well, that's not feasible because we're never going to have enough of it, or, you know, that sort of thing. And I would think that that might be crucial at this stage.
Did you want to say something?
Yeah, like I wanted to say something here, like, you know, like a lot of the materials, like you said, like, you know, it depends if that particular material will work in that certain area. Like, you know, that's why, like, you know, we need more definitely we need more information if that particular material is going to work or not. That's why, like, you know, we discussed about, like, you know, the ideal sourcing of the materials, and then about, like, you know, installing insulation and all. Like, the overall, what we are trying to do is, you know, build a low carbon building footprint. And, like, you know, how we can do that is by using these materials. Like, you know, these materials are, like, you know, one component of that, getting that overall, like, you know, low carbon building. So, like, what we tried to do in this presentation was, like, you know, tell you about all these materials that are, like, you know, good examples to be used. But as I explained in the challenges of, like, designing low carbon buildings, like, you know, like, we don't have a standardized system that specifically tells you, like, you know, if a particular material is suitable for this particular design in this particular temperature, or whether, like, you know, in this particular location, because a lot of factors come into play when you go into the detailed design process, like the sourcing, availability, cost, and all. Like, you know, a material that is abundant in availability in a particular country can be a low cost material, but cannot be in a different country. So, like, you know, certain things can be only figured out when we have more details of our project, or, like, you know, other information. So, like, generally, like, you know, like, definitely maybe we should have presented the disadvantages as well, but, like, you know, that's, like, it's only, like, so much information we can give in our
It's
general.
probably for the next talk. It was.
Yeah, you're probably right.
It was to prompt this exact type of, and a couple of things though that might be worth just taking note of. And as I said to you, you know, probably the first 10 years of the century, it was only dawning us and catching up with us how much trouble we're in, and how little attention we have been paying to the problem. But things have definitely ratcheted up very rapidly, and manufacturers here, well, in Ireland and in Europe, a lot of building materials come from Europe. They're coming under pressure to prove that they have taken steps to reduce their carbon footprint. And manufacturers are leading the role in a lot of cases. And the reason they're doing it is because purchasers are more aware of it, especially younger purchasers. It's a bigger issue for them. And we see it in the likes of American companies who will set a standard that they need for marketing purposes and for owners' requirements, but marketing being a big issue, and they will set standards that, you know, designers and constructors must achieve.
Absolutely, yeah. There's that to be considered too, yeah.
And obviously you work then within the limits of what's available to you.
Absolutely, yeah.
And in a lot of places you may not have alternatives, so you have to do something about that. And you know, these companies insist on LEED and BREEAM accreditation, which is a certified way of measuring your sustainable and carbon input, both in construction and in use. And they want gold standards. So it does come with an additional cost, but they're prepared to pay that cost because they know their future depends on having that level of
understand, yeah.
So in the particular instance of this funded project, well, maybe that's the next step that needs to be taken to take what we've talked about now and say, look, that's nice, but it would never work. We can't get it, or it's just not available to us. But then on the other hand, maybe that opens opportunities for people to say, well, what would it take to open some form of a hempcrete manufacturing plant? Or can we grow timber that in 30 years' time, we'll not only have a fuel, which would be a poor use of timber, but we can start producing building materials, because timber seems to be the way that all of these construction products, be they timber framed buildings or timber skins on buildings, but it seems to be the only product that's going to last out. So, growing timber, is that possible in countries? Manufacturing it, adding value to it, and then again cutting down the travel miles for these materials. And I think that's probably where the conversation and the discourse has to go.
Yeah.
Can I also ask one question?
Sorry, I'm going to have to jump off this call. I really apologize because I have another meeting. So I just want to thank you all very much. Do we get a copy of this presentation, Shamalina?
Yeah, I'll email it to Fran and he'll send it to you.
Okay, thank you. Very interesting and to be continued. Thank you very much.
Thank you.
Yeah, bye, Celine.
Thank
Thank
you.
you,
Bye.
Celine.
Thank you,
Bye.
everybody.
Bye.
Bye-bye.
Bye.
Can I ask a question? So basically, you said the design of the house plays a role in the emission of carbon that a building emits.
Yes.
So when looking at, we have an objective with regards to the project that we're doing. So we have an objective where we want to know the carbon emission that each material emits, meaning when looking at the carbon emission, we also need to incorporate the design of the house.
Yes, well, you should at an early design stage carry out an assessment of the carbon both in construction and in use. It's not mandatory here, but it would be good practice. And some clients will insist on it themselves, that you do an early stage assessment and then determine, can you revise it? Can you do things that would cut down on carbon? As I said, the orientation of the building could have an impact on its energy requirements.
Okay.
Yeah.
Thank you very much.
Yeah.
No, I understand. Thank you very much.
Yes,
I understand what you're trying to say.
Yeah. Yeah, so I hope I understood you properly there. So there is the national software here in Ireland that must be used. It's not for carbon assessment, but it's for energy usage, and you're obliged, it's a statutory requirement to actually carry out an assessment using the national, it's called DEAP software for housing, and NEAP for non-housing. But there's an obligation to use that software and to assess DEAP. Yeah. Yeah. And NEAP for non-domestic software. And you must assess a building using whichever the appropriate software is, and you must actually you must submit that for approval as part of the building control process in this country. Now, it's only related to energy. It's not. It does measure carbon, but it's only an asset tool. It's not. It's not a full-blown carbon assessment of the building. I hope that I hope I explained that correctly.
Yes, you did.
Yeah. Yeah. Okay. I'm not sure if it's possible to actually to issue it. If I'll do that if possible. It's available. It's available online. You may have to be registered to get it, but if I get my hands on it, I'll send it around, and people can have a look at it and just see what information needs to go in and what sort of results it gives out. It might be helpful.
Thank you very much. I would love that.
Yeah.
Okay.
Okay. I also have a question. I saw in your presentation where you spoke about blended cement, and I was interested I was interested more in the specifications, and I wanted to understand how is it different from the maybe conventional everyday the conventional everyday cement. How is it different, and how and how much is the emission compared to the everyday conventional cement? And I was looking at the stabilized mud blocks there, and I could see that they look like they are compressed, and I was wondering, Uri, are they compressed using a machine, or what are they used, or how are they compressed? And if anything that is used, or the machinery that is being used to compress those stabilized mud blocks, does it not emit too much, or like, yeah, everything that is involved with the stabilized mud blocks, if you have any idea or any information?
So in your normal cement, they use this product called clinker, which is the main reason for the high emission in cement. So instead of using clinker, you can substitute it with like fly ash, slag, or limestone. So that is the main product that reduces the carbon emissions in blended cement. So that is like the basic difference between blended cement and your normal cement. And like, if you want to like know the difference, so basically again, like, if depending on the use, like, if they're using fly ash, slag, or limestone, and like, what percentage they're using it, like, the carbon emission number will change according to that. So like, that calculation has to be done again separately for like, each different substitute material that you are using, and at what percentage you are using it at. And for stabilized mud blocks, like, those the mud blocks are basically made using molds, like, wooden molds, wooden frames, or wooden or steel frames. So basically they are like, put into frames, and they're like compressed at with it can be done in industries, or I think it can be done with like, manually as well. So, and then those compressed mud blocks are then like, dried out, and then they are used in construction as normal bricks. Is that what you wanted to know?
Yeah, I wanted to understand that. So when we say the stabilized mud blocks, we mean that they are the compressed earth blocks, right?
Yeah.
Okay, thank you.
You have a chart of carbon loading per material, sort of materials.
I actually have a Excel sheet of like, a lot of materials, like not just these materials. Yeah.
Yeah, well, that might be
I
any
can
harm if we
actually,
share that.
yeah,
You're
share
saying
that.
that Shaolima would have a chart, with I'm not
various materials, like
materials and their carbon footprint. So you could compare numerically one with the other. But again, that may be careful that it applies to a particular region, because it may, if they have to travel further, that could change. But at least it would give you a reading, visual reading, just to say, well, look, cement versus that in one particular country could be 10% lower or 20% lower or whatever.
Okay, understood. Okay, understand.
Again, we can share that.
Thank you.
Yeah.
All right.
Yeah.
Okay, Lemi and Mina, those are all the questions you had.
Yes, Sri.
Are those all the questions you had?
Basically, those are all the questions I had. With regards to the carbon emission part, I think they told us more of the technical aspects, which were basically what we were lacking.
So you got that solved now.
Yeah.
So we also.
Sorry, I was going to say that, if you do have follow-up questions, you can always pass them on to Fran, and then we'll try and address them as well. I'm sure there'll be plenty of thoughts afterwards that, why didn't we ask that, or so you can follow up with questions at a later date as well.
You can send it, you can email it to me, and then like, I can get back to you. If you want the formulas and all, I can send it to you.
That would be very helpful.
Okay, one last question. Can a blended cement be used in all the structures when building? And what are the advantages maybe when using the blended cement on the buildings or the structures?
Basically, you just replace your normal cement with blended cement, and it has the same function and same durability. Just like the benefit is it being a low carbon material, so the emission. So if you're using blended cement over normal cement, you will be reducing the overall carbon footprint of your building.
Okay, this is very interesting because, and like for instance, let's look at hemp. I've heard that with hemp you use lime because lime has the characteristics like its breathability and the flexibility. So with regard to blended cement, do you suppose that it could also be used to build structures such as hempcrete structures?
I think you'd have to check that, really.
Yeah.
You couldn't just say, you'd have to check the compatibility of them, of the materials.
So in blended cement, what you're replacing is the clinker with the other materials like the fly ash. So only a very small percentage of that gets changed in that. Let's say 40% or 30%, and depending on that, you get the different blending cement with different carbon emissions. So blended cement might not be suitable for hempcrete blocks. The materials need to also get along with each other.
Okay, understood. I think
adding on that, the most suitable binding material for hempcrete is lime. Building. Yeah.
Okay.
Yeah.
Do you want to leave it at that, Rhea, and then maybe follow up with questions?
Sorry?
If you had more issues to discuss, or do you want to just leave it at that and follow up then with additional queries as they come in?
I think what we can do is we can get both your email addresses, and then as we have queries, we can address them to you. That's the first point.
Yeah.
Second point is if we can please kindly the presentation that you've just done today, because there's a lot of things we learned. There's a lot of things we would also want to be referencing moving forward, even post this first phase of the research project of the catalog and start implementing in some of our designs in our buildings.
Yeah.
Yeah, thanks. Let me just write it down. All right, now that we have your email address, I think I will stay in touch with other things as and when the team has questions. Thank you very much. That was a really, really great presentation. We have learned so much, and we're going to share it with the institution of learning where we partnered on their research module for final year diploma architecture students who weren't able to be on the call due to various reasons, such as they just started their semester, so classes are still a bit of a mess with the schedule. But thank you again, and we will stay in touch definitely as soon as right now to ask for the presentation. So yeah, guys, you have something to say, or we can end the call?
Yeah, I think we're good. Thank you for being present here.
Yes.
And
I look forward to seeing you again.
yeah, and you can email me with any further questions you have.
Okay, thank you very much. Bye,
Bye.
Karen.
Bye, everybody. Bye-bye.
Bye.
Bye.